Here we have a circuit that has sources and resistors and an inductor in it. So this is an RL circuit. We're told that the switch has been in position B for a long time. So the switch has been over here for a long time, means that we've reached steady state and we have a fixed constant current in our inductor. And then at t equals 0, we're moving the switch to position A, and we'll have this circuit here. This side will get disconnected. And so we're looking for different descriptions of what's going on for t greater than 0, what happens after the switch has been thrown, but our starting point has to be the steady state, the starting state of the system. So we're going to start by looking at the circuit when the switch is in position B for a long time. So let's go ahead and start drawing that circuit. Before the switch is thrown, we have this circuit here. The inductor is connected to this voltage source. The current source is still there, but the switch is such that this is not affecting our inductor at all. So if we're looking for the initial current, this isn't going to contribute anything. If we want to know the initial current in the inductor, the best way to do that is to find a Norton equivalent, which we can do here. We have a voltage source in series with a resistor, so we can do a source transformation to find a Norton equivalent circuit. And so when we have this Norton circuit here, at steady state, the inductor will act like a short circuit, and then all of these 12 amps is going to flow through that inductor. And so that is the current at t equals 0 negative. And so since the current in an inductor is continuous, that will also be the current at 0 plus. Right after the switch is thrown, the inductor is going to hold that current to be constant for that first instant. After we use the initial circuit to find the initial current for 0 negative for the time before the switch is thrown, everything else we're looking for is for t greater than 0, and so we're going to need to look for the circuit that we have after the switch is thrown when the switch moves to position A. So we're going to redraw the circuit with the switch in position A. Once the switch goes to position A, we are breaking the connection over here, so we're going to omit this part of the circuit since it's disconnected from the inductor and it's not going to contribute anything more. Now that we have the new circuit, this is the circuit for t is greater than 0, we can look at the behavior of the inductor as time goes forward. We can see a couple things. We can see that as the inductor reaches a new steady state, we have 8 amps flowing here, and so as the inductor reaches steady state, we'll have 8 amps flowing through the inductor that way, because at steady state the inductor acts like a wire or short circuit. This 8 amps is going to be flowing through the inductor in the opposite direction as I, and so what we can say there is that the current as t goes to infinity is going to be negative 8 amps, negative because it's going in the opposite direction of our definition of I. We can also see that the resistance we have connected to the inductor is just one resistor, and that resistance connected to the inductor is then 10 ohms. If we know the total resistance connected, we can find the time constant of this circuit. So we found the time constant, and we found the final current, and so we can use both of those to find the current through the inductor as a function of time. And so we start with our equation for the current through an inductor due to a step response, which is what we have here. We have a change in current from one side to the other, so that's a step response. Both of those currents were constant. We know the short circuit, or the t going to infinity current. We know I0 is the starting current, and we know the time constant, and so we can have the current as a function of time. And in fact, this was part C, and this was part D of the question we're being asked. We can be asked whatever we want. This is the process that we're going to go through to find the current, and then we can figure out what we're being asked based on our calculations here. If we're being asked for V of t for t greater than or equal to 0, we can find the voltage across an inductor based on the current through the inductor. So we use the characteristic equation for the inductor. We know what the inductor current is, so we can take the derivative of that value, and we can find the inductor voltage. If we want to know the inductor voltage at t equals 0, we can evaluate that. And notice here we have a very high voltage at the very beginning because we have 12 amps flowing through the inductor at the very beginning and 8 amps flowing through that current source. If the current through the inductor has to be 12 right at the beginning, right when the switch is thrown, and we still have 8 amps flowing from the current source, what's going to happen is we're going to end up having a total of 20 amps flowing through that resistor, which is going to give us a voltage of 200 volts there. And recall too that the voltage is defined for an inductor as if it's in the passive convention. So if this is 200 volts this way, if we reverse the polarity, it would be negative 200 volts, which is consistent with what we found there. But this process to find the current, and then to find the voltage, and then to understand whatever else is going on in the circuit is going to be our standard process here. It's better to go through that process step by step, and then we can go back through and figure out what we're being asked in each step. Here, this was step E, and this was step B.